Okay, we are live here. Morning. Let's are we back? I think the internet just cut out for a second. Looks like it's stable now. That's funny. Okay. Starting today, here's the plan. We are going to first do a little bit of analysis on the experiments that ran last night. And then after that, I have a couple different methods that I want to integrate with Puffer. I want to do probably cosine annealing. That's an easy one. And I definitely want to do MUPI. That is the different initialization that makes it easier to scale learning rate. And I definitely want to look into that a little bit more deeply. First of all, let's take a look at a couple of these because we should have a few hundred experiments. Looks like there are some still running. And okay. Oh, that's very nice. Look at that. So this is, this is the completed hyperparam sweep. Let's now compare this to what we had before. Let's see if there's a significant difference. So this should be identical to our initial baseline sweep, except that this time we swept the atom parameters. People don't usually sweep those. But I have a friend in optimization who told me, yeah, definitely sweep those. You know, it really looks like it's about the same, doesn't it? I guess cost 84 maybe here. It's kind of tough to see. Let's put them side by side. Oops. Okay, so we'll side by side these. I mean, this is like a little better, but I don't even know if this is statistically significant whatsoever. Now, I guess the other thing that we can do, what are you trying to optimize here? So this is just more hyperparameter sweep. This is just on a quick breakout test end. The key here, though, is we're sweeping the atom hyperparameters, beta 1, beta 2, and the epsilon. So we were seeing basically if there's any value in tuning that, even in like the simplest case. Now, we have to run this type of stuff over way more environments, but this is just like initial, hey, is there something obvious here that people have missed? Because I have some optimization friends who tell me that there is. Let me look at there's some things we should look at here though to confirm what we're seeing. Where's the time? There should be a time one in here somewhere. This. Yeah, right. So this is total time steps, and then we have SPS. Okay, interesting. So it looks like the one on the right ran way faster. So did the one on the right did the one on the right, let me see why it ran faster, because if there's like one machine is faster than the other, right? That's the one issue with using wall clock as your time, is that if the machines are faster than the other, then there's an issue with that. But it can also just be that we didn't get lucky and discover the right hypers here. In fact, I think what we're going to do is we're going to just let's just take a point. Maybe we'll take a couple of them. I think this one's a little bit of an outlier. This one looks good. 24 to 12. This one's like nice and stable, right? And then here we'll pick a point. I just want to get a sense of what the hyperparameters look like and if they're very different or not. And I guess we'll take this point here. This is like the closest analog. 21,536. Okay, so this one ran way fewer samples. So these found like completely different hyperparameters. Ignore this. We get, this is like the current learning rate, because it got annealed. 512 M's only. This did 2048. Hi, I was wondering, oops, hang on. I was wondering if anyone has made any breakthroughs on completing Pokemon using PufferLib. The original project does use PufferLib. That was, you know, that's the Powered by Puffer project right there. Let me find it. Where's the blog? Where's the new blog? Where'd the site go? Where did the blog go? Oh, there it is. Okay. Yeah, see, Powered by Puffer. The compute for this came from PufferLib. The tools, like the library, the training code, vectorization, and everything came from Puffer. So we've been collaborating on this project since P-Dubs did the initial, beat the first gym release. It would have been a lot harder without PufferLib, because it would have been at least like 30-50% slower. Not to mention all our other tools. Okay, so here we have our betas. These are a bit different from the defaults. Small batch size, but fewer M's, so that makes sense, and actually proportionally fewer, so that's interesting. Shorter BPT horizon, about the same entropy. Lambda's way higher, gamma's very similar. Lower learning rate, gradient norm, batch size, cool. 3 update epochs. I mean, this is at least interesting in that it's dramatically more sample efficient, right? I don't think we've ever seen, maybe we've seen something solve this fast, but this is now like, I think this is far beating like the original sample efficiency of PPO. And this is still like maybe 300 times faster than the original. So this is kind of cool that we're winning on both fronts now. I think what I want to do first is let's go grab, I think we probably already have these hyperparameters in place. Let's just put these betas in and see if it helps or if it like really does change all the optimal hyperparameters. That'll be a quick experiment to run. Oops. This is frozen for some reason. There we go. Let's put this, it's not blocking the screen. I really got to get some overlays so I don't cover like the chat and stuff when I do that. Mess that up. Cool. There we go. And that'll only take like a minute. And then we will copy and, whoops. Something screwed up here. Oh yeah. I totally forgot about that. Okay, we'll do this on the other branch then. And then I'll fix that after. believe this is the one that this is a solving config. Kind of slow. This is kind of slow. I don't think these are the optimal params for this. Yeah, let me go get better params. Yeah, you can see actually here, I was using params for the new algorithm, which are different from the PPO params a little bit. See how this looks? Oh, and I actually, hang on, is this the wrong algorithm? Yeah, this is the wrong algorithm too. All right, we can start with this. This is like decent enough. Okay, here's our initial baseline. And now let's take our atom params. Are here. I like how it just makes up a number. Morning, what are you working on? I'm testing the atom hyperparam sweeps for now, and then we're probably going to do mu-p, different initialization stuff, and then we're probably going to do cosine annealing. So it's like a whole bunch of little algorithm things I've wanted to do. Maybe E3B after, we'll see. And there's GGAE stuff to do. There's lots and lots of things to work on. Gotta kick Puffer into overdrive already. How much did atom params help? They did something weird. They found, so they found a very different set of hyperparameters that solves in about the same amount of time, runs way slower, and uses way fewer samples. So it runs about half the steps per second, but it solves in like less than half the number of samples. Well, this is something. Well, you can't say epsilon has a big impact. We got to look at, I'll show you how we'll do that analysis in a second. So, I mean, it's hard to say if this is statistically significant. I'd have to run it a whole bunch of times, but like, maybe this is helping. All I just did here is I took the optimal runs atom beta params, and I just threw them on the existing breakout params. But I wouldn't call that a failure. Like, it's like, okay, maybe there's a little bit of alpha in the atoms. The sample efficiency thing was actually the most interesting, I would say. Maybe there's something with it reusing the same data. And we'll do a little bit of the ablation analysis right now, because why not? So what you do for that is a trick that I like to do. So we do cost, where's this? Cost less than, and we'll pick like, what do we say, 100? Maybe we'll do 100. Ah, shoot, the dashboard's glitched. Hang on. $90. Cool. All right, so these are all the fast runs. And now we can look at the betas from here. $97. What did we use? I think we did use that point. Yeah, 97. So it changed the beta from the original. 999. Oh, it increased it. It's a little bit annoying because I know that you can get a high score in that amount of time, right? With a beta like this. So this could just be sample bias. It looks like, if anything, though, maybe the beta 1 is a little low by default. I'm filtering to find the fastest hyperparams, because anything will solve it if you give it 5 minutes. Yeah, the thing that I'm seeing most here is that maybe this first beta needs to be increased a little bit from the default. I have all the runs over here. Okay, so we'll keep that. You know, we have that as the experiment and an option now. And then the next thing I wanted to see is this. We have 115-second solves with the new algorithm. This is still running as well. $62 seconds, 700 is pretty good. Let me think how we can think about this as well. Down to sample. Oh, I guess I left this in, so I was sweeping Adam in here as well. No big deal. Okay, so we're still up here to 900,000 steps per second. You know, with some of these faster runs. We getting 8K mini batch is good. Total time steps is reasonable. Batch size, pretty reasonable. Found a few of these num-ems. It didn't really go this way too much, but it's fine. I guess I would want to try the optimal breakout params real quick. I think if I just want to play with this for a second. Yeah, I kind of just want to play with the breakout params in this new algorithm for a few minutes, just to see if I can find anything interesting. It's always interesting when you find like very different optimal hypers for stuff like that. This is basically 100 mil, right? Mil. Why does this have cost 120? Didn't I just click this and had I'm confused here, hang on. $21,335. This opened a completely different window. Okay, this is good. This is the right one. 1024 Ms. Soon more of us are doing research more often. We should rank the puffer Ms by training speed and difficulty. Might be helpful. Low difficulty. The thing is that the training speed, you're going to be able to get it to be pretty decent on any of them. We're going to be using all of them, I would think, as well. And the only way to rank them is to do full hyperparam sweeps anyways. We gotta get more people doing research. Oh wait, is it 70? What's this? 71. It's only 70 mil time steps. And 2 update epochs. Okay. See how this works. Train with torch, deterministic, true. Whatever the default is, I think CleanRL has that on for reproducibility. I don't think that that would make any difference though, right? What does that param even do? I can go benchmark it. Here, let me get this in first. Dashboard's really annoying how it does this. Okay. Why does this look worse? Oh, I guess this is with P301. It shouldn't be though. I must have a difference in hypers or something. See, 830K. Okay, that didn't work at all. Two update epochs, 2 mils total steps, entropy, gamma, lambda gamma learning rate, gradient norm. These params all look fine, so what did I do? I must have done something. $50. So minute 13, a minute 11 or whatever. 970 KSPS. 1024 Ms. Yeah, something screwy here. Because that did not replicate at all. Unless I broke something in the meanwhile. I don't think I did. But this is sketchy because this should definitely replicate. I have something in the base config. I don't see anything. No, horizon's correct. Yeah, that's just bizarre. It's also a tad slower than before. Only thing I can think of. Get out of here, bot. Morning, folks. Doing some experimental analysis here. And hopefully coming up with some good tweaks for Puffer. I'm gonna have to run this experiment again because I got a completely different result here. It's possible this is just like an inconsistent set of hypers. It's also possible that the atom params actually matter. So there's the replication. Or is it this one? No, not this one, this one. So right here. Meantime, I will go look up the default atom params. It's 0.9 and 0.999, which is what I set it to. Is it the epsilon that makes the difference there? That's the only thing I can see is it's a very different epsilon. Well, we will see. It could also just be inconsistency in the seed. Some of these arcade M's are a little sketchy that way. We will fix that, but for now. Yeah, it's just seed inconsistency. Why atom and not atom W? Is there any evidence atom W is like consistently better? Decoupled. People don't even use weight decay at the moment in RL. That's one of the things I've been meaning to run some experiments on. But yeah, people don't even use weight decay. Yeah, so this would be equivalent to atom, I would think, without weight decay. And then we would have to try them both with weight decay. Okay, yeah, this matches. So it was just some seed noise. That's fine. I mean, that's cool that we have, what's this, 118. So that's 80-ish second solve. And now we can try, let me see if the new atom params made any difference. Look into learning rate schedulers. Yeah, actually, I'm going to do that today. That's part of what I'm going to do today if I get to it. Oh, that one? Is that just a scheduler? I thought that was a whole different algorithm. Yeah, I know, Lucas. Batches of parameters simultaneously. Schedule free. I've also heard about Muon. We can play with these. It'd be pretty easy to play with them. Let's get our like basic stuff done first, though. I think order of priorities today is I want to finish up this analysis. I probably want to do stuff on mu-p, and then I want to do optimizer stuff. I mean, this doesn't really count, right? This is what I'm doing here. This is pretty basic. Mu-p is this thing that LLM people use a bunch that lets you use the same sort of hyperparameters, or same learning rate in particular, as you make the network larger. Because I want to add the network size as a hyperparameter to the sweep, you know? We'll see what this does. So this is now the same experiment as before, so same optimized breakout params, but with the tuned atom coefficients. So it's apples to oranges, but the hope is that it just is better, you know, it's per environment. That'd be cool, yeah. I gotta stop like putting white background stuff on my chat. I've been really meaning to just get like a basic overlay made for this. Does that just crash everything right here? Is that what I'm seeing? It's bizarre. Again, though, there is some seed variance, so I will try it again. A few more experiments and we move on to mu-p. I just want to check this. I think it's going to be slightly more complicated than anticipated with this. We'll see. And then I wanted to try the latest version of the new algorithm on this with these params as well. Yeah, that's just awful performance. That's crazy. Okay. So it's not as easy as just shifting the params and calling it a day. Not quite so easy. So I made this cool modification late last night to P3O. I was having this problem where as you would increase the horizon, the allowable horizon, it would change the algorithm. It would make it so you couldn't reuse the same hyperparameters. Now it has an adaptive horizon. So it starts at 16, and you will see it increase once the score gets a little higher. And the horizon, in this case, is the number of samples into the future it's considering. Usually settles on. The horizon just tends to increase over time because it's based on what it can predict. So the farther out it can predict, the farther out it uses samples. Now these hyperparameters are not for this algorithm. I was just trying this. This doesn't seem to work particularly well with these hypers. It's a start though. Different from the horizon. Yes, it is. It's different. Okay, so it doesn't work with these hypers. That's what I was checking. I will run it one more time just in case there's like seed variance, though I highly doubt it. And I think we'll just go to mu-p so I can, not get stuck on this all morning. So I've had my eye on this for a while. This is the core graph right here. Is they find that normally the optimum learning rate changes when you shift batch size. Not batch size, when you shift the learning rate. Optimal learning rate changes when you shift the model size. There we go. Whereas here, they keep it pretty darn, consistent. So these are all transferable, it says. So any of these atom parameters Does anybody know there aren't follow-ups to this, right? This is still what people use, right? They have code for this? Let's see. Yes, they do. Okay, we'll use their library to start with, and maybe we'll like integrate it properly if it works. Yeah, so it wasn't just seed noise. Cool. How did they get a 3-letter package name? Basic usage. In model definition, replace output with mu readout. I might want to make a branch for this real quick. Not really. Okay. So we're gonna do this one. Multi-discrete continuous. Yeah, it's this one. Mu readout, hidden size, and action space n. That's it. They don't change the rest of the model. Oh, I think that theirs will change your initializations for you. Wait, I gotta read these comments. So, instantiate a base model. Optionally use torch distx deferred init. Okay, that's like if you don't want to double initialize a big model. Instantiate a delta model that differs from the base model in all dimensions that one wishes to scale. Instantiate the target model, the model you actually want to train. This should be the same as the base model, except the widths could be potentially different. Okay. When model has same parameter shapes as base model, model behaves exactly the same as base model. When model has same parameter shapes as base model, model behaves exactly the same as base model, which is in PyTorch's default parameterization. This provides backwards compatibility. Oh, okay. So this is so what this does then is you set up like what model you want mu p to use as a starting point, and then it keeps that the same, and it scales around that, I guess. That's fine. Base and delta models do not need to be trained. Okay. Do you need delta model? Kind of a weird thing that they've done. Whatever, though. I think it should be fairly easy. We'll see if it works with the RNN. The policy. You passed the policy in. That's annoying. We can just hack something for now, I think, right? I mean, this is kind of crazy. Let me look at their source, see how complicated it is. Confusing code. So this is just a multiplier, fine. Knit. What about this? Uniform. drop-in replacement for uniform. Normal, drop-in replacement for normal. Let me see. So then why do they have, what is it that they need this crazy thing that they're doing for? Set base shapes. I think I have to read a little bit more in the paper to figure out what this is actually trying to do. We need to modify initialization of the last layer and its learning rates of the first and last layer as well as of the biases. Initialize so eta is master learning rate. We highlight in not purple, but whatever. The difference is of two parameterizations. Scaling with width n of the parameterization. We often insert multiplicative constants in front of each appearance of n. We highlight in purple the differences in the two parameterizations. So hang on. And W1 or eta, not n, but whatever. I'm trying to figure out if there's just like a simple how does this work that I can just implement without having to do this mess. Oh, okay, so for the MLP in section 3, so they gave a specific initialization here. And they said, hey, if you use this instead, then it transfers. This is a little bit annoying because of the way that I have my policy set up. Wider is always better. You should always see performance improvement with width at any point in training. Okay, this is actually possible. This would be very useful. I think we will just try to force this their original for now, and then we'll go from here. I don't really like adding this as a dependency, but I think for dev branch, for playing around with stuff, it's fine. Because we'd like to add this as a flag anyways. Okay, let's try this. This. Let's actually do this one first. Like this, right? Policy and then base policy. So we do args policy hidden size is equal to 1. Base policy. Okay, and then we do delta model, which just has this attribute changed or whatever. Where is it? Just like this. This will be delta policy. Let's go to 2. And we'll do C. see, policy. All set base shapes. This stuff is, yeah, this goes at the top. We don't need this. Actually, I think you could even do easier than this, can't you? Hang on. We can make this easier. Hang on. I can do it right here. That's not that bad, actually. I don't like having more stuff like this in the demo file, but I think for dev branch, whoops. I think for dev branch, this is fine. Now I need just these set base shapes, right? Policy, base, policy, delta. Okay. Replace your custom init, if any. Replace with the same. Okay, I think we'll leave this as is. Make base. They don't even call this, do they? They just call set base shape, so we can just do that. This should be called before optimizer definition, fine. And the optimizer. All we need is, let's put this here. Move Atom. Cool. So this hopefully, this should train the same way as before, according to the authors. let's not screw this up with a new algorithm or anything. Well, base shapes has extra names. And base shapes dot decoder dot weight. Is there a get base shapes anywhere? Or make base shapes? Did I miss something? They imported it. No. So I set the base shapes here. Base shapes has extra names. Let me see what I did. Do you still have to do evaluating of decide if it's worth it or not? I think that there's definitely something in that vein of research, I will say. And it got us a really good result on Snake. So I'm probably going to merge that into dev. And I cleaned up a bunch of stuff in dev, so it's a lot easier to like try different methods as flags. We don't want to keep them all long term, but what I really want to do soon, I want to get all these methods in, right? And I want to start running them on way more environments than I currently am. I'm mostly just running quick stuff on Breakout and Pong these days. I really want to be running stuff on like Neural MMO and all the other M's we have. Oh, here it is. You messed right here. This one, delta. Boom. Policy value has infinite. Change f fan out to an infinite dimension. Okay. ability. So I think that you need to set base to be 128. Oh, this didn't work. What the hell? Let's run it again. But this did not work. Let's see if it's just jank. I also have one other idea. I think I might have messed up. What is this heavy ball optimizer you linked me? Let's just ask Twitter. I have a group chat with the guys that did the heavy ball stuff, so. Wait, wrong chat. Hang on. See if we get any reply on that. And did this fail? Yes, this still fails. So we got to figure out a couple things with this then. First thing, base to 128. Do that. Okay, let's see if that changes anything. Hey, welcome. So I went to implement the thing that we were talking about yesterday, and I realized it's actually kind of hard to do that without changing the learn target of the optimizer. I can show you what I ended up doing. I came up with something I think is pretty cool. Because basically anything, so I confirmed for certain that the reason that it doesn't train at longer horizons is it's not because of the bias, it's just because of the noise that you get from those extra steps. So what I did is I made it variable horizon. Let me find it. Yeah, so right here, horizon starts at 16. Yeah, the variance ends up being greater. Well, it's the variance in the value function for whatever reason. It actually doesn't matter as much if you clip the advantage. Like, there's way less noise than that because, like, if the rewards shift a little bit, it's fine, right? Because you're computing a sum. But it's way more of a big deal in the advantage function because that's like a per term loss. But anyways, what I did is I just take the first value where it is greater than 95% of the standard deviation you would expect from random. So like I'm looking for the first one where you basically have no signal, it's all noise, and then I clip the horizon to that. And then in the loss, I just get rid of the terms that are either up to the horizon or sometimes you give it a few extra elements because you have to start training those values. And this actually, it still doesn't work as well as PPO, but the cool thing about this is now you can provably, you can set that horizon parameter however large you want, and it will not screw up your training. It strictly allows you to learn longer horizons as you're able to predict them. So that's pretty cool. So we got that going. And now we're doing other algorithm stuff. Currently trying to get mu-p working, and it's not working. Mu-p is this thing that LLM people use a lot. They change the initializations and the optimizer rates such that the optimal learning rate stays fixed as you change the network size. So it's a really nice technique for like stable training, though it doesn't seem to be working right now. Yeah, because I have this layer in it right now, right on this. I have listening, studying for an exam. Best of luck. I'm glad I no longer have to be doing that. Let's see this. There's also the orthogonal in it and the recurrent net, right? Let me think about this. Oh, yeah. No, we haven't. It's such a pain, though, because initialization is one of those stupid rabbit hole topics, because the search space is massive. I guess I should probably look at what the LLM people are doing at the moment, but I don't know if there's much, I don't know if there's much to be gained there. There are, like, other places I would look first. Let's do this one first. Oh. I mean, the thing is, those methods just don't fucking work, right? So, like, the people that are like, oh, well, we're going to use this because it's explainable. This actually happens very often in industry, by the way. Like, people in finance will do this or whatever. And it's just like, oh, well, we need it to be explainable so we can rationalize the decisions. It's like, okay, well, every decision it makes is wrong. So you can just explain that you're stupid, right? Because you used a bad model. But it's like, oh, but, you know, it made this bad decision because of this, and that. Like, I don't know. Look, interpretability work on neural nets is good. But yeah, the other methods just are not very promising. I mean, the thing with the like regulation is the whole thing is just dumb because a lot of explainability work also just gives you the illusion of understanding anyways. Like you're not gonna understand the decision from start to end, right? It's like when somebody tries to explain to you why they did something. It's not actually why they did something. It's an explanation of why they did something. So it's like, oh, neural nets aren't explainable. Congratulations, humans aren't explainable. Now it's a little bit reduction, like it's a little bit reductive, but still. See if this works. Mu pi, it doesn't have orth. Does it really not have orthogonal? Doesn't have orthogonal. Lovely. Oops, that's the wrong language. Why does this screw this up so badly, though? It's kind of crazy, isn't it? What version? I probably should be back on those because I do need to put some weight back on. The problem is I need to put about 10 pounds back on that I lost from hospital. But like in order to actually not just get fat doing that, you have to be training really hard. And my work capacity is still like way, way down from what it used to be. So I'm kind of just like eating normal food as much as I can. Yeah, that mug, like, you really have to be training hard for that mug to do what it's supposed to do. Um, and I'm training, but I do not have the capacity to train hard enough to sustain like 1,000 calorie surplus. Yeah, this is just tea. The mug is a pretty legitimate. It's a pretty legitimate thing though. If like you just need a ton of calories and don't have the appetite, it's pretty damn good. It gets you most of your protein for the day. Not terrible. I'm trying to think why this thing wouldn't be working right now. I guess it's just because it doesn't have the initializations I would want. Mhm. Mu atom. I mean, it's like it stops training, doesn't it? Try this. Oh, maybe it's this. Hang on. Times equals 2. It's probably this. It's probably that you need the annealing and you're doing it wrong. How do you do this though? How do you do this? Hang on. Let me just see if this does anything. 9, 9. I'll be right back. I'm gonna use the restroom. I'm back in a minute. Yeah. That's annoying. It still doesn't fix it. See this? Does it feel like that was better? Minute 22 seconds. 368. Yeah, there you go. Yeah, this is fine. Oh, actually, it is correct here, right? Yeah. We'll see how this goes. That looks much better. Is this the run that I'm looking for? I think it is. Does it just get stuck here still? Hmm. Okay. So it was just the scheduler being wonky. That's a nice improvement. Perfect. So now we have mu p working. According to this, I should now be able to just use a larger network and do better. Can I just do this? Not in wall clock, but in samples. I should be able to just do better. Expected 128. What's that? Got 512, expected 128. Hang on. Oh, I think it's input size. Hang on. Yeah, it's input size. So this takes hidden size, but the RNN takes input and hidden size. Yep. What size? Oh, and also, before I screw this up, bars hidden size. Two. This one actually goes here. Hang on. There. Now we have the scaling factor, right? Mu p. So this is now 512 hidden dimension with the same params, other than the tweaked learning rate. We'll see how the curve looks. It's the fact that I quadrupled the model hidden dimension. Yeah, a bigger model doesn't seem like substantially better, but also not substantially worse. It's actually... Does this even make sense that it's still that fast? Oh, it's not that fast, right? Because now it's going to run... Is it not going to run eval and be a little slower? Yeah, okay, so it is a little slower. Cool. But now we actually have the option to do that. Why would torch compile help? It should help less for the bigger policies. I mean, that's a 2 million parameter model that's running at 575 mil in eager mode is pretty damn good. Why would it help less for larger models? Because you have less of a percentage of the time devoted to CUDA kernel launch overhead, which actually the standard torch compile doesn't really help with. You need to like fiddle with CUDA graphs a bunch, which I haven't done. It's probably a good, a big source of perf improvement, but it's kind of a mess at the same time. And we'd have to be able to also fully trace the backwards pass, which is annoying. You can't trace the backwards pass as it is right now. Okay, but these are good results. Very brittle, yeah, exactly. And these are good results, though. Yep. So I think that let me see, it's 11. Do I want to play with anything else initially? Let me try a couple more things. I think it's still cosine annealing is the most commonly used, right? Yeah, it's still cosine. Let's try cosine annealing first, I guess. I think I'm gonna just I'm gonna leave most of this fiddling until after lunch. I'm gonna get some food, I'm gonna do a couple things, and then I will be back with more dev. I think that's what we're gonna do right now. So I'll be back soon. We're gonna do today learning rate schedulers, finish MuP integration, see if that works. We're gonna integrate model size with hyperparameter sweeps. That's gonna be cool. There's gonna be some more testing around that. We might do some work on my new advantage function. Several like algorithm side things and cleanly integrating all this with the dev branch as well so people can play with it. So I'll be back soon. And in the meantime, if you're interested in following my stuff, follow puffer.ai, start the GitHub to help us out. Join the Discord if you want to get involved with development, contribution, or just using it in general.